Hello, welcome to part 8 of the linear and nonlinear relationships topic. Today we'll be looking at circles. I think this is a really interesting topic, so I hope you'll hang around. Sorry, couldn't resist. Alrighty. Circles are one of the most naturally occurring shapes that we see around us in the world. Their equations may be not as natural. Before we jump into working out the equation of a circle, let's talk about the definition. A circle is made up of all the points that are an equal distance from some fixed point. So no matter which direction we go in from our centre, the distance is always the same. And you guys know that as the radius. Let's now draw a circle that has its centre at the origin. On our circle, we're going to place a point, P. Let's put it here. And this point P is a random point that has coordinates x, y. While we don't know much at this stage, what we do know is that the distance from the centre out to this point P is the radius of the circle. So let's call the length of this r. Because we know that the coordinates of P are x and y, we can drop a vertical line down to the x-axis, to this point x, and a horizontal line across to the y-axis, to this point y. Now we can see that there are some right-angled triangles that have been formed. Let's look at this one in particular. The base of this yellow triangle has length x, and the height of this triangle is y. Using Pythagoras' theorem, we can say that the smaller sides squared and added together should give us the hypotenuse squared. Or, in other words, x squared plus y squared is equal to r squared. This is actually our formula for a circle that has its centre at the origin. But what about if our centre is not at the origin? What happens then? Let's draw a diagram to set up the situation. Our new circle does not have its centre at the origin, but at some other point. Let's call it HK. So the x coordinate is h, and the y coordinate is k. Now just like before, let's set up a point P with coordinates xy that lies on the circle. The distance from the centre of our circle out to this point P is still just the radius, r. Creating our right-angled triangle, like before, gives us this. However, the base and height of this right-angled triangle are no longer x and y. Instead, they are these distances here. So how would we represent these distances? Well, this is the distance between h and x, or x take away h. And over on the vertical side, we have y minus k. So, applying Pythagoras' theorem, we have the two shorter sides squared and added together to give us the hypotenuse squared, which is just the radius squared. Our first short side is x minus h, and our other shorter side is y minus k. And this is the equation of a circle that has its centre at hk and a radius of r. Let's do two examples now to practice our skills on circles. What is the equation of a circle that has centre -3, 4 and radius 5? First, let's have a look at the centre, -3, 4. In the equation we just came up with, the centre was represented by hk. So, by comparing values, we can see that h is equal to -3 and k is equal to 4. What about the radius? Well, the question tells us the radius is equal to 5. Now that we have this information, we can go ahead and use the formula that we just came up with. X minus h squared plus y minus k squared is equal to r squared. Substituting in our three values, and we get the following. X minus -3 all squared plus y minus 4 all squared is equal to 5 squared. Tidying this up, the two negatives make a positive, and on the right hand side of our equation, 5 squared is equal to 25. And that is the equation of our circle. Let's have a look now at example 2. Find the centre and radius of the circle with equation x squared plus y squared plus 6x minus 2y plus 6 equals 0. Now this equation does not look like the form that we've talked about. X minus h squared plus y minus k squared equals r squared. So we're going to have to turn it into that form. And the way we will have to do that is by completing the square. So let's first separate the x terms from the y terms. And if you recall from completing the square, we need to add in our own number to each of these so that we can use the perfect square rule. We will also, before we go too much further, subtract 6 from both sides of the equation so that we get -6 on the right hand side. If you do need any help on completing the square, be sure to go back and check out the quadratics review video. The method involves taking the middle term, halving it, and then squaring that number. So 6 divided by 2 gives us 3, and 3 squared gives us 9. So we are going to add 9 in here. But whatever we do to the left-hand side, we have to do to the right-hand side of our equation as well. For the y's, let's take 2 and halve it. 2 divided by 2 gives us 1, and 1 squared is also 1. So for this we will add 1. But whatever we do to the left, we must do to the right. The reason we have done this is to create some perfect squares. X squared plus 6x plus 9 is equal to x plus 3 all squared. Y squared minus 2y plus 1 is equal to y minus 1 all squared. And on the right hand side, we can tidy up and get +4. Now we have our equation in a form that looks a lot more like what we want it to look like. We can now say that the centre is equal to the point -3, 1. And the radius is equal to 2. Because 2 squared is 4. If you're wondering where we got the -3 from for the centre of the circle, x plus 3 is x take away -3. So with those two examples done, that finishes our lesson. Thanks for watching.